very good morning, everyone. Welcome to the second session of Malaysia Process Control Society Webinars 2021. Similar to last week, this morning we are very privileged to have Professor Jibao from the University of New South Wales. He is also the associate editor of Journal of Process Control. This morning or this afternoon in Sydney, we are going to listen to his research entitled Distributed MPC based on the distributivity theory. Without further ado, Professor Jibao, we invite you and over to you. Thank you.
Thank you very much, Agus, and thank you very much for inviting me to this webinar series. Yes, my topic today is a distributed model predictive control based on the distributivity theory, and this work was supported by the Australian Research Council to Discovery Projects funding. Today, my talk, I would briefly introduce UNSW and the process control research at the University of New South Wales. And then I would give a quick introduction to the distributivity theory. And then we come to the topic of distributed model predictive control based on the distributivity theory. And then I would, if time permits, I would also talk about some contraction theory based distributed economic model predictive control. First, University of New South Wales, UNSW. I know some of you graduated from University of New South Wales. UNSW now is branded UNSW Sydney, is located in Sydney. We have two campuses. One is in Sydney, one is in Canberra. This campus in Canberra is called UNSW Canberra. So what do you see here? There are the photos of one is the photo of Sydney, the Harbour Bridge, you can see that. And this photo shows the campus of UNSW. So the building with the UNSW logo on the top, that's our library. So if you look a little bit far, you can see the Coogee Beach. So the university is located in a very good position. So it's about 50 minutes from the international airport, 10 minutes from the beach, the Coogee Beach, and 15 minutes from the CBD. So this is where the university is. We have roughly about 55,000 students, including about 14,000 international students, 9 faculties and 75 schools, roughly a little bit less than 3,000 academic staff called faculty members. The annual income is about 2.1 billion Australian dollars. I think it's roughly 6.6 billion Malaysian dollars. The university was founded in 1949 and now is one of the top universities in Australia, a member of a group of 8. And according to the QS World University Rankings, we were ranked 44 internationally in 2021 ranking, and the Faculty of Engineering is the largest in Australia and number 37 in the world according to the 2021 QS ranking. The School of Chemical Engineering, we have research areas. We focus on those research areas, including energy, particularly and energy conversion and storage. We looking at the new materials for the batteries, and one of the areas is actually the flow batteries, and also get involved as well. And environmental technologies, particularly water, membrane separation technologies, and food, health, and medical science and technology is another area. And also we do research in macromolecular and interfacial engineering. Of course, we also do research in the field of advanced process systems engineering. That includes process modeling and process control. The process control group, we have 3 research fellows at this moment and 8 PhD students. And by the way, I think the photo is pretty old. I think you can still see some previous students in the photo. And what do we see here is Dr. Michael Tippett pretending doing experiments. We conduct research in both the control theory studies and the control applications. In control theory area, we work on one is the dissipativity theory-based control. That includes the distributed control and the decision making, flexible manufacturing based on contraction theory, but also the dissipativity theory as well, and fault detection and fault tolerant control. And recently we started some research topics on big data, machine learning, and process control. We try to integrate control theory with machine learning. In the application areas, we have been working on aluminum smelting process, some monitoring, and advanced control. And recently we started a new project on the virtual energy storage. And the idea is to use the smelting cells as virtual batteries, because the aluminum smelting process is very energy intensive. In Australia, we don't have a very large aluminum industry, but the aluminum industry consumes more than 13% of total electricity in Australia. So typically, if we got one smelter in one state, then that smelter would consume about 10% of total electricity in that particular state. So the idea is we do demand management. When we have power shortage, we reduce the production rate, reduce the consumption of power. When we have excessive power, we increase the production rate. So in that case, the smelters or smelting cells can be used as virtual batteries to balance the demand and supply and to help stabilize the grid. And also it helps to reduce the cost for the aluminum smelters. The other applications we've been working on, including flow batteries, particularly the vanadium batteries. Been working with Professor Maria Skalas-Kazakis, also from University of New South Wales, who invented the vanadium batteries 25 years ago, more than 25 years ago. And we've been working on the monitoring and the control of those flow batteries, and also the control of distributed energy storage systems, where we have many battery systems located at different locations, and how we coordinate those battery systems. So our research has been funded by the Australian Research Council, ARC, Emirates Global Aluminium. By the way, that's a company in Dubai. They produce about 4% of total aluminium in the world. And they have a huge power plant as well. They have their own power plant of about 3 gigawatts. And ACAP, the Australian Coal Association Research Program, and CSIL. Now let's start a topic on the distributed model predictive control. Let me start with some challenges in plant-wide control. We know that if you look at a chemical process, typically they have many process units interacting with each other through the mass, energy, and mass and energy flows. And in that case, what you need to do is to control the entire process, which is called plant-wide control. Now, the modern plant-wide systems can be quite complex. Often they have tens or sometimes more than a couple of process units. And I just now mentioned the material recycle strings and heat integrations. They're very good to make better use of materials energy. But from control point of view, that's bad news, because they actually introduce positive feedback that leads to strong interactions among process units. So if you look at, we have a process diagram here. This is the diagram of a tennis instrument process. The red lines indicates the mass recycles in the system. And also, most process units are nonlinear. So that makes the control of modern chemical plants a very difficult task. Now, traditionally, we use centralized controllers. So we basically treat the entire plant-wide process as a single complex multivariable system and control that process using a multivariable controller, or if you use model predictive control, then you have a complex single multivariable model predictive controller. The problem of that is that when the scale of the chemical process becomes large, then the complexity of the designing of such a controller becomes more and more difficult to manage. And one of the issues really, the model itself becomes very complex. How do you get a reasonably good model for a complex process, and also the control design. And in the industry, people also use decentralized control approaches. One of the ways to do that is we divide the plant-wide processes into many subsystems, and we have one controller that controls each subsystem. Okay. The problem of these decentralized control systems is that often they do not have much communications among them. That often leads to poor control performance, and sometimes even cannot guarantee the stability of a plant-wide system. So the distributed control would be a natural middle ground solution. So it's, but before I go there, let me have a quick look at it as the formulation of model predictive control. I guess many of you probably have heard of model predictive control, MPC, and what I have here is a problem formulation of MPC. So first, what we do here is that we do optimization, which decides the control action in real time. And we have, obviously, we have a cost function. So this cost function in the standard MPC, often we use a quadratic cost function as those cost functions you use in optimal control. So it is typically a quadratic function of control error and the control action, together with the final cost. Subject, we need to optimize the cost function and solve for the control actions in the over a receding horizon for the next, for example, n steps. The optimization obviously is subject to the model of the process, and of course all the manipulated variables are constrained. So all the control actions must be have to belong to the feasible control action set, which is described as U here. Okay, now as I mentioned just now, that one way to control the plant-wide process is to use a centralized MPC. So in that case, the model we have here describes the behavior of the entire plant-wide system. So it'll be a very complex model. And one of the good things of model predictive control is that it can deal with operational constraints. This is particularly important in modern chemical processes where we often operate near the constraints. And the MPC problem optimized for n steps in the future, but only implement the first step. Okay, so in the next sampling time point, it does the optimization all over again with the updated the new state information of where we are. But this kind of MPC approach can become very complicated and difficult to implement when the plan-wide system gets very large. So one of the solutions is distributed MPC. The distributed MPC is actually somewhere between decentralized control and centralized control. So if we divide the plan-wide system into many subsystems, and we can have one model predictive controller to control each subsystems, but those controllers, they would communicate with each other so that the actions of those model predictive controllers can be coordinated. Now, in that case, obviously, the key issue is how to coordinate the model predictive controllers. There are a number of different approaches. One is called cooperative approach. So the idea is that individual controllers will manipulate their own local control variables and manipulate variables to optimize a global cost function. The global cost function may represent the requirements for operating the entire plan-wide process. And this approach obviously requires iterative optimizations and can be very complex when the scale of the problem gets large, because all these individual model predictive controllers, MPCs, they have to they transmit their planned control actions, and based on the transmission, they redo the optimization, and they have to do it iteratively until they reach a certain agreement. And also another issue would be the stability issue, because exchanging the control trajectories alone is not sufficient to ensure global stability. That was as reported by Lawrence and Stewart in 2008 paper. Another approach is called a non-cooperative approach. The non-cooperative approach, in individual controllers would optimize their own local cost function, but they don't optimize a global cost function. And this is the more scalable. However, it does not optimize the global objectives. So in many cases, if you think of the plan-wide control, then what you want to do is to minimize the global plan-wide cost function, but the non-cooperative approaches typically do not guarantee that. So from that, for the global objectives point of view, the non-cooperative approaches typically can only deliver a suboptimal solution. And but it often leads to a much simpler control design, because the communications among the individual controllers and the iterative optimizations are significantly reduced. To certain cases, could be in certain cases that we do not require iterative optimization at all. But what we need to do here is to be able to determine the effect of the interactions and find a way to deal with the interactions. Okay. Speaking of the model predictive control, recently the trend is that a lot of emphasis has been focused on the economic model predictive control, because the model predictive control, you can minimize the cost function. And just now in my previous slides, you see that the cost function is a quadratic function of the error and control action, or quadratic function of state and control action. So certainly bears the question, why not we put in a cost function that represents the economic cost of running a chemical process. So the cost function ideally would have a unit of dollars. Okay, and in response of the changing feedstock supply and the market demand, so process operating strategies, including the operating conditions, needs to be frequently updated to improve the process economy. So that's the driving force of the economic model predictive control. Now, on surface, it's very easy. We just replace the cost function with a true cost. But often that leads to many challenges. Number one, the cost function is no longer quadratic or positive definite, not necessarily. So many existing stability conditions for model predictive control that requires positive definite and quadratic cost functions may not be valid anymore. So we need to have a new stability condition or stability design to ensure the stability of the economic model predictive control. Okay, and certainly when we look at the implementation of economic model predictive control in a distributed way, then the distributed MPC, EMPC, would require the plant-wide stability and the performance conditions to be satisfied. And these days, that the idea of distributed economic model predictive control has been implemented in other areas rather than just chemical processes. One of the areas we have been working on is the distributed energy generation and storage. So if you look at the diagram here, we are looking at the many different consumers, but each consumer may have the solar panels on the roof as the energy generator. They may have the energy storage like batteries, and so each of those kind of consumers called prosumers because they produce energy and also consume the energy. So they form a network, obviously, and typically there would be a microgrid. And we are looking at the situation, for example, different consumers. One is that consumer here could be a large commercial building. So you look at a significant power consumption or generation. They may belong to different owners. So when they operate, they may want to optimize their own selfish economic benefit. And how we coordinate the operation or control of those buildings or active consumers so that it does not cause the instability in the microgrid. Depending on the energy storage capacity, if they have very significant energy storage capacity, then if each consumer would optimize their own economic benefit, they may be able to hoard the energy. So they buy the energy when the price is very low and store that and sell them sell the energy when the price is low in the future. And then the market in the microgrid is like a stock market. If you don't have any way to regulate that, then it could lead to instability of the microgrid. And also those consumers, they have limited information sharing. So what you look at here is really distributed decision making. And when we store the energy, either it's generated by the solar panel or we buy the power from the microgrid, or when we sell the power. Okay, so what I'm going to talk about is one of the approaches that developed for the distributed model predictive control or distributed economic model predictive control, which is non-cooperative, and we look at the plant-wide process from a network perspective. So we see that as a network. And we study the interactions using the dissipativity theory. And our approach would allow the controller and the process topologies, arbitrary controller and process topologies. And that achieves the plant-wide stability and suboptimal plant-wide performance. And later on, we extend it to achieve the plant-wide performance, optimal performance as well. And each controllers can be can have a own selfish objective, So this is called self-interested DMPC, or they can optimize the plan-wide performance. Okay, so let's look at the network approach. So what do we do here is that we see the process network, the plan-wide process, as a network of process units. So for example, P1, P2, P3, P4, they are different process units. And each unit or subsystem is controlled by a controller. So C1 controls P1, C2 controls P2, so on and so forth. And the controllers, they talk to each other to form a controller network. So the idea is that we use a network of controllers to control a network of process units. Okay, and all these controllers can be autonomous, so that we can design the controllers so that in a way they are more fault tolerant. If the communication breaks down, they at least they can still make decisions. Not optimal anymore, but at least to ensure the stability. Okay, now for the process models we use to describe each process units. Now this is a typical process model that I think you'll be very familiar with. So we say, okay, we have U, which is the manipulative variables, Y, which is the controller variables, and X state variables. And the model which describes the relationship between the input and output and the states. So this is a linear version, this is a nonlinear version, but no matter what, we're looking at information flow between the sensors and the controllers. But when we look at the plan-wide control, now obviously we need to deal with the interactions, and the interactions are through the physical mass and energy flows coming into a process unit and leaving a process unit. So what do we have here? UPI means the mass or energy flow coming into process unit I. YPI represents the mass and energy flow leaving the I's process unit. Okay, so obviously we also have manipulative variable, which is denoted as UL here, and also the sensors or controller variables, which is denoted as YL here. So this is the representation of one process unit. But obviously, if you see that, we have a two-port system representation. So we have two sets of input outputs. The one set represents the physical mass and energy flow. Another set is the information flow, as we saw just now in the previous slide. So typically the information flow, they include the sensors, which measures the intensive variables. Okay, now, so if each process unit can be represented using a two-port system, then we can have a controller which take the measurements of the process controller variables and manipulates the local actuators. And those controllers can talk to each other. So we also have another set of input and output of the controllers representing the communications. So in that way, the process network and the controller network can be represented using this control block diagram, where P1 to Pn, they are the models of each individual subsystems or process units. C1 to Cn are the models of each individual controllers. Okay, so basically they're the block diagonal systems, both of them. Also, for the processes, so actually we have another input, which is disturbance. So the disturbance goes into different process units. HP is a topology matrix representing which output from which process units is connected to which input of another process unit. Okay, And HC is a topology matrix of the controllers. It has a very similar thing, and it basically says which controller is talking to which controller. Okay, so the proposed dissipativity-based approach, it's a scalable approach. The whole idea is we use the dissipativity property or dissipativity theory to study the interactions effect and the stability condition of a plan-wide process. Okay, so whole idea is that we do not focus on the letting the controllers to negotiate with each other and to come to the an optimal operating condition through iterative optimization, but rather we try to put a law on each controller, just like in human societies, that you have the law there and they say that these are things you can't do, and you can do whatever other things to maximize your own selfish objectives. Now, so this law, of course, is a numerical law that constrains the behavior of the controllers, and each controller can optimize its own selfish local objectives subject to the law. Okay, so in this case, and obviously that we need a law which has sufficient details so that the distributed controller design is not too conservative. But we also don't want use the models themselves because it's too complicated. So what do we need here? Perhaps is a kind of a property of the subsystems that can be used so that we can determine the conditions or the constraints on each controller that ensures plan-wide stability and control performance. The question is, which property? Okay, now the property we are looking into is the dissipativity property. Now the concept of dissipativity was, I think, was first published by J.C. Williams in 1972. That's a very long paper, actually. I put the reference here, only part 1, but I actually got part 1 and part 2. That's an extension of, at that time, an existing concept called passivity. I think the first book I've read about passivity was 1966 by Desert and Vidyasagar, which is called Input-Output Properties. Now, I'm not sure how many of you are familiar with the Lyapunov stability and the Lyapunov functions. So in Lyapunov stability, we basically says, okay, now if we got a state space representation, that how do we study the stability of a given equilibrium point? Is that let's see whether we can find a Lyapunov function which is positive definite, and if you can show that a positive definite Lyapunov function, its a derivative with respect to time is less than 0 when x travels on the trajectory of the system, then we say that the equilibrium point is stable. But if you see the Lyapunov stability, obviously it has nothing to do with the input and output, because the stability is nothing to do with the input output. We're talking about the stability of a state of equilibrium. So obviously, you're talking about a free system. But when we look at the plan-wide control, we are dealing with the interactions, and obviously the interactions are as a result of the input and output of each subsystems. So obviously we need a concept that connects the stability with the input and output. So it has to be an input-output property. Okay, so here the definition I used here is not in the original 1972 paper, but rather a later paper because it's easier to explain. Now, if we have a nonlinear system given in equation number 1, let's assume some equilibrium points and let's assume the equilibrium point x is 0, then it says that this system is dissipative with respect to a function defined on the input and output, which is phi here. So the phi is a function defined on the input u and output y. This function is called a supply rate. And we have a storage function, which is something very, very similar to the Lyapunov function. The storage function is defined on all the states, and the storage function is typically positive definite, but in the dissipativity theory, the definition is positive semi-definite. But that's a minor differences, but conceptually we don't need to worry too much about that. So it basically says that if the change of the storage function is bounded by the supply rate, then we say this process is dissipative with respect to that supply rate. Now, if we look at equation number 2, it basically says that we are defining a property, input-output property of a system, such in a way that about how its Lyapunov function is affected by its input and output. Okay, so we just call the Lyapunov function storage function here. So for linear systems, actually, if you know the model of the process, if it's A, B, C, D, and actually we can solve a matrix inequality given by equation number 1 to determine the supply rates and the storage function of the process. So basically the problem becomes a convex linear matrix inequality problem, which is called KYP lemma. And in this case, for example, P is the coefficients for the storage function. So it's very much like the Lyapunov function. And the QSR, they are the coefficients of the supply rate. And this condition was extended to nonlinear systems by Hill and Moran in 1976. But that leads to solving a number of nonlinear inequalities that make things a lot harder. In practice, it will be quite difficult unless we have some special types of nonlinearities like polynomial systems. And the supply rate function, that we can have all sorts of different supply rate functions, and different supply rate functions describes different input-output properties. For example, if the supply rate function is y transpose u, the dissipativity condition is actually a passivity condition. It basically is about the phase condition of the process. So the process is linear if it's passive, then the phase shift of the process will be somewhere between -90 degree and +90 degree. If it's nonlinear, then this passivity condition means that the process dynamics is a minimum phase, or its zero dynamics is stable. We can have all sorts of different supply rate. For example, the input fee for the passivity. So the supply rate is, as I said, is a function of input and output. But in this case, we have the particular type of the input-output condition or supply rates. That output, if we got an output feedback passivity, then the supply rate is minus y transpose y plus gamma square u transpose u, and it basically represents an input-output stability, or in other words, that the gain of the system is bounded. So if it's non-linear, we say it's an L2 gain, but in this case, L2 gain has to be bounded by gamma. So from this, you can see that the input-output stability condition can be represented using a dissipativity condition, or certain the dissipative with respect to the supply rate. And if we combine the the first three types of different supply rate conditions, we can have a more general condition which is called QSR dissipativity. So if you look at the passivity, it's Y transpose U. Input feed-forward passivity, you got a Y transpose U and a U transpose U. Output feedback passivity, got a Y transpose Y, U transpose U. And obviously, they're all about quadratic functions of the input and output. So we can have the QSR dissipativity, which is basically a quadratic function of the input and output. Okay, so that's more generalized than the first three different supply rate conditions. So it's kind of a, somewhere in between. And typically, Q needs to be symmetric, R needs to be symmetric because you got a Y transpose QY, and obviously Q has to be symmetric. And the QSR dissipativity is basically represents a combination of the gain and the phase conditions. And what's interesting here is that because the dissipativity concept applies to nonlinear systems, so the QSR dissipativity actually represents the combination of the gain and the phase conditions for nonlinear systems in an extended sense. Particularly, if Q is negative definite, then basically means this process is L2 stable. In other words, the gain between the output and the input is bounded. Okay, so if we go back to the previous slides, it basically says that if you have a model of linear system, how do you determine the QSR dissipativity? So the parameters Q and S and R, which is supply rate, and also P, which is the coefficients for the storage function. So from this, you can see that the dynamic properties of a system are captured by the supply rates. But there's one issue, of course. If you look at here, we already listed 4 types of different supply rates. Clearly, for a given process, the dissipativity property is not unique. So it basically depends on what you're looking for. So if you want to have the gain conditions, you get the output feedback passivity. If you want to see the phase conditions, you look at the passivity condition. So if you look at the QSR, actually you have infinite number of different supply rates for a given process system. So if you think about control design, it's really objective driven. So you need to look for the supply rates and dissipativity conditions which allows the stabilizing control design. Okay, now one of the most important reasons why we study dissipativity is that if we look at the interconnected systems, the dissipativity of interconnected systems can be represented as a linear combination of the dissipativity of individual subsystems, particularly in terms of the storage functions and in terms of the supply rates. Okay, now if we look at this closed loop system, we have 2 subsystems, H1, H2. Let's assume that the H1 is dissipative with respect to Q1, S1, R1, the supply rate, and H2 is dissipative with respect to Q2, S2, R2. Then we can show that the closed loop system, if we form a closed loop, then obviously we look at a dissipativity from the R, in this case, I would be the input, to Y1 and Y2, okay? Now, so the dissipativity of the closed loop system, we can have the Q of the closed loop system given in this box. So you can see that's it's a linear combination of the coefficients of the supply rates of H1, H2. And the R is given by the S of the closed loop system is S1 minus R1. And the R of the the closed loop system is R1. So just now I mentioned that if the Q matrix is negative definite, then we say we know that that system is stable. So in this case, if we have the overall Q matrix of the closed loop system is negative definite, then we can ensure closed loop stability. And from this, you can see that the closed loop stability condition is simply a condition based on the supply rates of H1, H2. And also, it's a linear condition, so it's very easy to use. Okay, so that's one of the reasons why we're interested in the dissipativity condition, because we can extend that the stability condition for two interconnected systems into a network system. So in that case, we can have a very large network system. If we know the dissipativity of each individual subsystems, and we know how they interconnect with each other, so the topology of the interconnections, then the overall dissipativity condition is simply the supply rates, so simply the linear combinations of the supply rates of individual subsystems. Of course, all the coefficients of the linear combination depends on the topology, depends on how they were interconnected. Something I forgot to say here is that the storage function of the overall system, of interconnected system, if the storage function of H1 is V1 and the storage function of H2 is V2, then the storage function of the closed loop system, overall system, can be just V1 plus V2, or can be a linear combination of V1 and V2 with arbitrary coefficients like alpha V1 plus beta V2, as long as alpha and beta are positive. Okay, so that's why we use dissipativity conditions, because in this way, we can use the dissipativity properties to derive the dissipativity conditions to explicitly deal with the network topologies of a process and the network topology of the controllers, and that allows the plan-wide distributed control design. Okay, so here's just a simple example. Let's assume that we only look at the process network for the sake of argument, because if you look at both the controller network and the process network, the representation becomes very complex. So in a plan-wide process, you remember we talked about that each process units can be represented as two-port system. We got the physical flow, like the energy and mass coming into the system, disturbance coming into the system, and the afferent flow of energy and mass out of the system, and the manipulated variables U, L, and the sensor output YL, so two-port systems. So we can write a dissipativity condition for each subsystems. Here we don't consider controller at this moment. So obviously we have two outputs, and we have we have two sets of outputs, Y and YL, and we have three types of inputs, UPI, DI, and ULI. Okay, now let's assume that let's write Y as YPI and YLI. So Y includes both, given here. So obviously let's assume the storage function is psi. So psi I, the storage function for i's process units. So obviously the supply rate can be written in equation number 1. So this is the Q part, this is the S part, and this is the R part, because we have 3 inputs, 1 output. Okay, and if we have n different process units, we can stack them up, and we can have an open loop dissipativity condition for all the process units. But in this case, that we have Q represents different Q matrices in each subsystems. So Qi, I from 1 to n. and S and R. So we basically can have everything represented in a matrix form given by equation number 2. Okay, so now if we have the network topology HP represents how the process units connect each other, then we can write the overall dissipativity condition with that the process interactions or the interconnected with that topology of HP given here in equation number 9 and 10. So obviously this is the overall Q matrix. Okay, so remember Q and the S are they are the matrices which contains the supply rates of each individual subsystems. HP is the topology matrix. So from this new Q matrix, we can tell the effect of the interactions among the process units on the plant-wide dynamics. So we have the dissipativity conditions of the plant-wide process, and in particular, this is the overall plant-wide Q matrix. It can tell you about the stability of the plant-wide system. In this particular case, we assume that we don't have a controller in first. So we're looking at the open loop system actually. And it basically says that if each individual subsystem is stable when you interconnect them, do you have a stable plant-wide system? The answer is depending on the topology of the plant-wide system, depending on HP, depending on whether this matrix overall plant-wide Q matrix is negative definite. Okay, and also that if we assume that as I said, if we assume we don't have controller, so UL is 0, then the above condition is reduced to equation number 10. Then it also shows that if I don't have any control action, how would the disturbance affect the process outputs? Because now we have a supply rate as a function of Y, which is the controlled process variables, and D, which is the disturbances. So it tells you whether the disturbances would affect the control output significant or not, because for any process which is dissipative with respect to QSR dissipativities, we can estimate the L2 gain. So basically tells you the sensitivity of the process outputs to the disturbances. Okay, of course, the purpose of control design is to design such an UL to minimize the disturbance effect on the process outputs and ensure the stability of the closed loop system or the plant-wide system. The concept of dissipativity is also quite useful in the sense that there's a link between the dissipativity and thermodynamics. Now, for any of you who has ever worked on Lyapunov's design for a nonlinear systems, that you probably remember that's always very difficult to determine the Lyapunov function. So because the Lyapunov stability is a sufficient condition, not necessary. So if we can find a Lyapunov function such that dVdt is less than 0, then you can show the stability of equilibrium point. But if we can't find such a Lyapunov function, then the study is non-conclusive. So the nice property of the dissipativity property is that there's a link to the entropy. So Eric Eastie published a paper, I think, here I list the 2002 paper. That's very comprehensive paper. But I think the first version, I think, was 1994. The first result was 1994 paper on the link between the dissipativity and the thermodynamics. In his paper, he called it dissipativity passivity, but the concept is exactly the same. And the good thing of that is then theoretically for chemical processes, to determine the storage functions, you may not need to do this trial and error methods to find a storage function. You can look at the entropy functions of the process and come up with a storage function. And it links process design with control better. So potentially that we could look at the dissipative property of the process, so we know, okay, so what kind of performance we can achieve. And that dissipative property, because it's based on thermodynamics, so it's directly linked to the process design. Okay, and we also worked with Eric, tried to extend his results, because the original work that the results are very useful and very insightful, but not always ready to be used in control design. So at that time, the slogan was, let's put physics back into control. And so we actually work together, and we extend that result so that we try to put the control back. So that was the paper we published in 2013. A little unfortunate that we put the control back, and we sort of kicked the physics out a bit. So the storage function we had does not have exact physical meaning anymore, which is a bit of unfortunate. Okay, so let's come back to the control design. So, the whole idea of this dissipativity-based control design is that we describe the plant-wide stability and performance conditions using dissipativity. So just now I already mentioned that you look at the Q matrix, and the negative definition of Q implies the plant-wide stability, and then you can also have the L2 gain from the disturbance to process output represented as certain dissipative condition. For example, the QR dissipative condition, like output feedback passivity conditions. And then we translate that dissipative condition into the dissipative conditions that each controller has to satisfy. And then we do the controller design. Okay, so this idea, we developed both the general distributed control framework and the framework for the distributed model predictive control. So this is some early studies we had using the plant-wide stability and performance represented using the dissipative properties and do the control design. However, when we did that, when we tried to extend that results to MPC, a distributed MPC, we had problems. Number one, as I said just now, is that the whole idea is that we represent the properties of each subsystems using its dissipativity. But the dissipativity property can be very conservative. For example, if I have, just now I said, we know we can have output feedback passivity condition that represents L2 gain. I can have the L2 gain of the plant-wide system from the disturbance to the process output. But we all know that if you've got a dynamical system, they often, if you look at the gain or the frequency response, that you would have a peak somewhere at a certain frequency, and the L2 gain represents the largest possible gain. So if you think about the sensitivity function from disturbance to process output, and we want the sensitivity function to be the gain to be very small, but at certain frequencies, it will be very large. It will be larger than 1. So no matter how you design the controller, the chance is at certain frequencies, the control error would be larger than without a controller. But does not necessarily mean that the controller is doing a bad job. It only means that if you use the overall L2 gain to describe the performance, that's a bad idea, because you look at the worst case scenario across all the frequencies. So obviously that's too conservative. Another problem is that the MPC controllers, remember just now I mentioned that the idea is we got a process distributivity, the controller distributivity, and if the process is linear, and we can have the matrix inequalities, and if you got ABCD of the process, then we can use the matrix inequalities to determine the distributivity, the storage function, the supply rates. But for controllers, you do not have a model, because MPC controller action is the result of online optimization. So we do not have a controller in a closed form. So we need to have, in this case, the distributive theory cannot be directly applied. So that's why we looked at the behavior approach to the systems theory, where we try to determine the supply rates and the storage functions as a function of the trajectories of the input and output. So if we extend the input and output, so if the input is u of t, if we extend the code u hat of t, so u hat of t is basically the input at different time steps. Let's assume you got n2 steps, and the output is also, we look at the trajectory. So y hat is a trajectory output. Then we can use a new ways to define the supply rate and the storage functions. So where the storage functions, supply rate can be a quadratic function of the input and output at different time steps, given the equation number 2 here. Okay, so y hat is the y1, y2, y3, so on and so forth. And u hat is u1, u2, u3, so on and so forth. Okay, so in that case, we can write the, if we put them together, we can write the supply rate, we call it Q5 because that's in quadratic form. In this form, equation number 3, which is called the quadratic difference equation. Okay, quadratic difference forms, QDF. And we can do the same thing for storage function as well. So in this case, that we do not need the state information, but rather effectively we infer the state information from the input-output trajectories. Okay, and in this case, we can also write storage functions as y transpose t, because the y is the original output. Q zeta eta u of ut. So, sorry, actually, I think I have a mistake here. It's actually y transpose u transpose phi zeta eta y transpose u transpose. Sorry, that's a typo in this equation. So where zeta and eta, they are operators representing a forward step in time on the left and the right hand side of phi. Okay, now once we use this storage functions and supply rates as a function of trajectories, we can have much less conservative stability conditions for planar-wide control, because in this case the supply rates actually are dynamic supply rates, and this allows also, because it's less conservative, that allows the controller network to be designed completely just based on the distributivity of process units rather than their models. Okay, and that leads to even the planar-wide performance description can be much more detailed. So it's like we got a frequency dependent the H infinity performance, where we look at a H infinity norm with the frequency dependent weighting functions. And also another good thing of that is this QDF representation, because the supply rates a function of the current step of input output and the future steps, that fits in the model predictive control framework very well. Because in MPC, we need to predict what's going to happen in the future. And here, basically, we need to solve the future input and outputs, and in this case, that the supply rates of the controller or the closed loop system in the QDF form works very well, because it'll be a function of the the current and the future steps of the input and output. Okay, so we published some major results on this topic. That the first paper is about the general theory of the dynamic supply rates and stability conditions and applications for countywide control. And second paper is about the controller synthesis. And the third one is the extension to the distributed multi-period control. Okay, now, so let me, I think I already talked too much, but let me briefly explain the idea of the dissipativity based multi-period control. That just now I mentioned that there's two challenges. The first challenge is conservativeness. We solve that problem by introducing the dynamic supply rates, or QDF supply rates. And the second challenge we had, we solved that by defining dissipative trajectories. Because just now I said that in QDF we use we define the supply rates and storage functions based on the trajectories. So we can do it for the controller trajectories as well. So if we have a storage function of the controller which is Q phi C, the dissipativity condition basically says that the change of the storage function is bounded by the supply rate of the controller. So UC here is the input to the controller, YC here is the output from the controller. But if we assume that we have no knowledge of the storage function of the controller, then this inequality can be reduced into the summation of the supply rate to be positive semi-definite. Okay, so if we have the supply rate condition, and then you could determine at any time point whether the MPC controller trajectory is dissipative. Okay, so this result is actually quite different to the usual definition of dissipativity, because it basically says that I just need to check the dissipativity condition on that particular trajectory I'm driving towards, or I'm currently working on. This does not imply the dissipativity condition of the general behavior of the process. So it does not be satisfied for all possible inputs. Okay, so basically we can derive the same idea. So I can skip this slide. Basically, it says that using this concept, we can have very similar results as the dissipativity stability design as we had before for the model-based control. So here if we have the supply rate of the controller given by here by this matrix, and then this is the condition that ensures the closed loop stability. Okay, and we basically can have, as I said, the performance bound to be weighted H infinity norm conditions. So we can introduce a weighting function W, so that if we want to see minimize the disturbance effect on the each individual process outputs in the YP, the process interacting output, and the controller variables, then we can have a weighting function, which is a function of frequency. So we may say, okay, I want this norm to be small at low frequencies, but not necessarily high and small at high frequencies, so that we can have less conservative design. Okay, so let's just summarize. I think I already talked too much, so I will speed up a little bit. So what we do is we represent the plant-wide performance and stability conditions using the QDF, the quadratic difference form dissipativity. And then we convert the plant-wide dissipative conditions into the dissipative conditions that each controller has to satisfy. In this case, that we basically need to solve the dissipative condition for each subsystems or controllers. But remember, the plant-wide supply rate is a linear combination of the supply rate of individual process units and individual controllers. Okay, so eventually we can solve those conditions together, and each condition is a linear matrix inequality, as convex inequality. We can solve them simultaneously so that we can determine the dissipativity condition of each controller. And then we can just use that condition as an additional constraint on the each individual MPC. And that condition would ensure plan-wide stability, would ensure the plan-wide performance. For example, the gain from disturbances, all disturbances to all the controlled outputs. And then you can have each individual subsystems of the controller has its own objective function. So in this case, we don't have a coordinator. This is a democratic autonomous approach. The key issue is, of course, the conditions on the feasibility solution, because you can always add some constraints to ensure plan-wide stability. The question is whether it is feasible. Okay, so for each controller, we can have the MPC represented in this way. So the cost function, the models, the only difference is the model now is a two-port system. So the state equation is more complicated, but we also need to have a dissipativity constraint on the controllers. Okay, I don't have time to go to the details about the feasibility, but we studied that feasibility issues in this paper, in the paper published on ARCHE journal in 2013. Okay, so we also extended the about framework into multi-time scale plan-wide control, because the process units, different process units may have different time constants, so how we deal with that. And also the flexible networks, because from time to time, we may have to reconfigure the plan-wide process network topology. One typical example is in polymerization processes. Often we need to change the configuration of the plan-wide systems to introduce additional recycle strains to produce the polymer products with different specifications. For example, molecular weight distribution. Probably I would touch the last point very quickly about nonlinear distributed economic MPC. As I mentioned earlier, that a very natural way of thinking of the MPC is economic MPC, because you're doing optimization anyway. So let's use a cost function which represents the economic cost. But if the process is nonlinear, the economic MPC problem is a typical nonlinear control problem, because you have to drive the process to different set points at different time as a result of online optimization, or to follow and optimize the trajectory. Okay, but and those trajectories may change from time to time depending on the market demand, depending on the cost of utilities and so on and so forth, or cost of the raw materials. So fundamentally, it's a nonlinear control problem, but it's actually more complicated than a normal nonlinear control problem, because normal nonlinear control problem assumes that we are doing the control design for a given equilibrium point. So if we design a Lyapunov function, the Lyapunov function is designed for that particular equilibrium point, and the control design would ensure the stability around that particular equilibrium point, drive the process to that particular equilibrium point. That works fine if we do regulatory control, if you have a constant set point. But if the set point is varying all the time, it doesn't work, because when you change the set point, in theory, you have to redesign the Lyapunov function. You have to redesign a nonlinear controller. It doesn't work. So fundamentally, if you want to do economic MPC, the economic MPC has to be set point independent or reference independent. Okay, so of course, if we do distributed economic MPC, yes, you have to be reference independent as well. So the idea is to introduce the contraction theory and look at the differential dynamics or displacement dynamics. So the idea is, the basic idea, I don't have the time to go to the details, but I would like to explain some basic ideas. The basic idea is that if I look at the trajectory, let's look at a process and look at the trajectory x of t. Then x of t, obviously, and we have different trajectories, and they're a function of time. But we can also parameterize those trajectories as x of st, where s is an implicit parameter. But for example, if my current trajectory is this one, corresponding to s equals 0, and my desired trajectory is this one, which corresponding to s equals 1. So what we can do is we can parameterize all the possible trajectories in between using the parameter s. So in that case, the trajectory x is a function of s and t. T is the time, s is that parameterization. And in that case, we can rewrite the state space equation. And then we can look at something called differential dynamics or the displacement dynamics. So this work was initially introduced by Romeo and Slotin in 1998. So we can look at the differential dynamics around that trajectory as delta x, delta dx dt equals something multiplied by delta x plus something multiplied by delta u, where delta x is partial x partial s. So it's basically the displacement on x, and the delta u is partial u partial s, the displacement of u. So the whole idea is we want to design the storage function as a function of not only the state x, but also the displacement delta x. So the storage function becomes delta x transpose m of x delta x. And the dissipativity condition needs to be satisfied for all possible delta x and also x. Okay, so we can basically, like, this is basically the contraction results. And eventually we would have the controller law is delta u as a function of delta x. And when we try to implement the actual contraction, the actual contraction is the integral of delta u along the something called geodesics, which is basically as a result of a parameterization of all the trajectories. Okay, so I don't think I will have time to go to the details, but what we did was we extended that result to model predictive control. So what we did was we have we extend the dissipativity condition we had into the differential dissipativity. So the differential dissipativity conditions, there are conditions on x, input and output, and also delta x, delta u. And then we do the integral of that dissipativity condition, so we can get the condition that which is in the state space, and that condition would be the constraints that we use to ensure the convergency of all the states to the desired values. So today I don't have the time for the details, but you can find the basic framework of this distributed planar-wide control based on the differential dissipativity in a paper we published in 2017, and then later on we developed the results on the distributed economic MPC, and these three are for self-interest distributed MPC. Not necessarily good for planar-wide control, because for planar-wide control, obviously what you want to do is to optimize the planar-wide cost function, so minimize the planar-wide cost. But it will be useful in the scenarios like the energy storage networks, and if each subsystems are owned by different owners, so they try to optimize their self-interest. But in that case, you want to ensure the network stability and also performance, like you've got disturbances, the disturbance needs to be rejected. And we also extend that results to the plant-wide optimal distributed economic MPC, and that was the recent results. Well, when we do that, we cannot get away from iterative optimization. So, because we try to minimize the plant-wide cost, so you have to negotiate with each other. But the idea is that we minimize the iterative optimization as much as possible, and also we use the dissipativity, the supply rates as a vehicle to do the negotiation. We negotiate the dissipativity so that we can reduce the level of iterative optimization as much as possible. Okay, I think I already talked too much, so I skipped the example. Let me go to the conclusions. So we found that the dissipative theory is a suitable tool for developing a unified framework for plant-wide control design using the distributed controllers, distributed multiplicative control, and nonlinear distributed economic multiplicative control, and they're relatively scalable, and because we can have the autonomous controllers that often leads to more reliable solutions. And the proposed approach can be extended to distributed decision making and the control of smart plants in those places that we have the smart plants can produce. We have the flexibilities in the quantity of the production rate, the quantity of the products produced, and the specifications, the variable specifications, depending on the market demand, and also depending on the cost of utilities and the cost of the raw materials. Okay, so I think I should conclude here, and I would like to thank you for your attention. And if you've got any questions, I'll be more than happy to answer those questions.
Thank you, Professor G, for your comprehensive presentation. It's like we got 25 credit lectures of your DEMC. Okay. Anyone? Now it's a Q&A session. Do you have any comment, opinion to Professor G presentations? Please welcome to ask anything. Professor G, maybe I can start with my questions.
Okay.
You know that in the network system theory, splitting and merging normally is the one of the concern. So if the network splitting is necessary, how could we maintain the trade-off between stability and optimality?
Right. Now, the approach we develop, stability, we can ensure that because we use now when you split the plant-wide systems into subsystems, one of the things which is very important is the topology, is how they interconnect with each other. So the stability was ensured by using the dissipativity theory, because we can write the plant-wide stability conditions in terms of the dissipativity, and that supply rate condition is function of the dissipativity of each individual subsystems and the interconnections, how they interconnect. So if the plant-wide stability condition, the dissipativity condition is satisfied, that ensures the stability. So that's fine. And also the good thing of that is because the plant-wide dissipative condition is a linear combination of each individual ones, and the coefficients are based on the topology, and And typically topology is constant. And so you design the process, how the process units connect to each other is constant. So that part can be easily done. And actually the very nice thing of this is we can deal with arbitrary topology of the process network and the control network, which is quite different to some past existing approaches, where when they studied the decentralized control, they formulate the decentralized control problem as a control problem with a centralized control problem with the controller structure constraint. So they say, okay, the control has to be block diagram, for example. And in that case, the problem is very, very difficult to solve because it becomes NP hard. It's non-convex. But because we use dissipativity condition, and we don't use the models directly, we use the dissipativity conditions of each individual subsystems, then the overall stability condition becomes a linear condition. We can solve that using linear matrix inequalities. So it's not it becomes a convex problem. It's actually quite easy to solve. But your part question about optimality, that's a problem. So typically, this approach that in the beginning, what we saw was we say, okay, the plant-wide performance can be the gain from disturbances to the process outputs, and we want to minimize the gain, so the disturbance effect is minimized. And then when we look at the optimization, we look at self-interest optimization. So because each MPC is optimized its own self-interest. So in that case, each self-interest you can optimize that, but the plan-wide overall cost function is not guaranteed until our very recent work that we like this one. Let me go back a little bit. So in the beginning, we basically implement this approach for self-interest DMPC. So all in these approaches, we assume that each subsystem, the controller of each subsystem, only optimizes its own cost function, but we guarantee plan-wide stability. And until we, this recent work, when we look at the plan-wide cost, and that requires a bit iterative optimization that comes back, because there's no way that you can ensure the plan-wide optimality without iterative optimization. I think there's only one exception was Frank Auger's approach. I'm not sure you have heard his talks on the dissipativity-based distributed control. And I think he was also talking about dissipativity-based distributed economic MPC. But his problem formulation is very different. His problem formulation was that he does not have the interactions, physical interactions among subsystems. In his formulation, the interactions is really about the relationship between the global cost function and the local cost function. So he formulated the problem as if you got many subsystems, and each of them has its own cost function, J1, J2, J3 to Jn, and the overall cost function is simply the summation of individual cost functions. And he came up with a dissipativity-based approach. He represents the cost functions using the supply rates. Then he decomposed the supply rates. So in that way, he said, okay, now now we got a different cost supply rates for each individual subsystems, and so different costs for each individual subsystems. As long as you could optimize that individual subsystems, then you automatically optimize the global cost. But it's a different scenario as what we discussed here, because the interactions, direct physical interactions among subsystems, they are not present in that framework. So that framework is typically a framework for distributed decision making. But he could guarantee the planet-wide optimal cost. That's a very good question. Thank you.
Yeah. Then those leave the second question, Professor G. The dissipativity is greatly affected by disturbances, either internal or external. And given the current scenario that the there are cyber physical interactions, are there any resiliency criteria to absorb this, cyber physical fault?
That's a very good question. I'm not sure whether one area could be potential. Would it be can we link to the information theory? But that's something I haven't studied so far. But of course, that another way to work on this direction might be to further explore the link between thermodynamics and dissipativity, because the thermodynamics properties are that's about a physical system, and all chemical engineers, I think many of us are chemical engineers, are very familiar with, and we probably take care of those thermodynamics when you design a process. So if we link the thermodynamics with dissipativity, and then we have opportunity to design the chemical processes which can be easily controlled, and further on, that if we later on, as you said, if you look at the cyber physical systems, may lead to a better integration of the information part and the physical part of the cyber physical systems. And our recent studies, we didn't go that far into that area, but the recent studies working on is try to use the dissipativity theory in data-driven control. Because you see that we can have dissipativity for the trajectories, and data-driven control, big data-based control, based on the behavior framework, is that we describe the process dynamics using the trajectories. So that gives us a vehicle to deal with the dynamics features of the data-based control, or big data-based control.
Sure. Thanks, Professor G. Anyone else? Maybe if you have any opinion, comment, you can post your comment in the chat box. Otherwise, you can unmute yourself.
Hello, Professor. So you mentioned about data-driven approach and control. So me seeing this approach, I see that the DE MPC can be seen as like a reinforcement learning as an agent in an environment. So what's the role of reinforcement learning in this type of approach?
That's a very good question. Personally, I haven't worked much on the reinforced learning. Our current work is pretty much using the machine learning tools to determine, for example, the dissipative properties of the data trajectories, and then use that to determine the stability constraints we should have in data-based control, particularly something like data predictive control, like very much like model predictive control, but it's based on data, not based on the model. But I believe that we can use that the distributivity condition to be integrated to the reinforcement learning, feedback control, because again, because the condition here is a quadratic condition on the trajectories of the controller. So in theory, it doesn't really matter how you get the trajectory, whether you use optimization, real-time optimization, or you use a neural network. So you can put the additional constraint on that. The question is, how do we incorporate such a constraint in training the neural network for reinforcement learning? That's one thing. But I think it's a very good question, very good question. And the second issue is that you see that in my entire talk, there's I talked absolutely nothing about the probabilities. And in a reinforcement learning, obviously that will be a very important issue there, right? So that would be something, be very interesting to see whether we could do some further developments and see that how we deal with how we train the reinforcement network to also subject to the distributive condition and to deal with the probability conditions. I'm not sure I have answered your question, but I think I haven't, because I haven't done too much in the field. I just think that it's a very good question, and that's certainly one of the directions we should work on.
Okay. Any further comment?
Yes, good afternoon, sir.
Yeah. Yes, go ahead.
Good afternoon, sir. Can you hear me, sir?
Yes.
Yes, please proceed.
Okay. Thanks, Prof, for the excellent presentation. My interest lies in how to harmonize this theory within the existing software, say Aspen Plus software. Because I am working using Aspen Plus, and I have read some of these papers on the activity. So I find it challenging to harmonize it within Aspen Plus. So I'd like to have your insights into how we can harmonize this.
Sorry, I could not hear your question very clearly.
My question has to do with harmonization of the theory within existing software, say Aspen.
I guess did you hear that question clearly? Can you? I think
yes, I couldn't hear clearly as well. Yes.
Oh, you couldn't hear very well.
Yeah, can you repeat the question, please?
Maybe you were too close to the microphone, and I think the microphone. Okay. Yeah.
Okay, let me take it again.
Yeah, maybe you can lower your voice a little bit. I think that's maybe you saturated.
Okay.
I could not hear that clearly.
Okay. The question I just asked is that how do we use this theory? Obviously, one needs to write some codes to actualize this theory in reality. So, but if you are using a software, say Aspen software, now, because I have tried to do it by using your theory in existing software. So I'm thinking if you can give some insights into how to harmonize this, use the theory of distributivity in existing software like ASP.
You mean how we use that together with some software?
Yes, 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 Prof.
Certainly that, you know, I don't, so it really depends on the purpose of this this exercise, right? So you use the
Okay.
software to simulate the dynamics of the process, either?
Yeah.
And or use that to simulate the performance of the control design, you know?
Yeah.
I haven't implemented the algorithms in Aspen Dynamics, but I think you would be able to. I'm not sure how complex the user defined modules you can have in the Aspen Dynamics, and I think you should be able to implement the model predictive control algorithms in the Aspen Dynamics if you are allowed to plug in a user-defined module. I'm not sure I understand your question correctly.
It's okay. I got what you are driving at, Prof. Actually, my thinking is that one can write code for the theory, say in MATLAB. Okay, then one then transfer it to the Aspen, because Aspen provides a way to integrate a third party software. So the problem so far with me is that you mentioned something like the matrix that defines the stability of that particular process. Okay, so when I try to transfer it to ASPE, it's not actually working out.
Okay, I'm not exactly sure whether I understand your question, but
Professor G,
I will send the question later.
do you mean that you're looking at doing simulations of the planar-wise systems, and you have different process units, and you may have a convergency issue? Is that what you're saying?
Yes, that's what I'm saying. Yes, that's what I'm saying, sir.
Okay, so you are saying that is that possible for us to use the dissipativity theory to improve the convergency of the simulation?
Yes, 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 that's what I'm saying.
Professor G.
It's actually a very good question. But the purpose is quite different than control, though.
Professor G.
Yes.
Let me maybe a bit paraphrase. I think we have a similar question in the chat box. I think what he meant maybe is like how to implement this dissipativity theory for the EMPC and implement it in the different software like maybe MATLAB or Aspen. So I think they are interested to maybe employ the algorithm, but they are wondering how to maybe implement that in the software.
Okay, right. So our current development mainly we implement using the MATLAB or MATLAB and Simulink. So basically, because the majority of the algorithm is the particularly for the first parts, like the linear and distributed MPC, the majority of the algorithms are actually the offline planning. So to determine the dissipativity condition each MPC controller needs to satisfy. and that condition is actually just a quadratic conditions on the controller's trajectory. So at the current time point, or at the case time point, this is the condition on the controller input output in the past for n steps. So it's a quadratic function of that, and that condition needs to be greater than 0, for example. So that would be an additional condition implemented in the MPC. So that part of implementation is actually quite easy. We use MATLAB, but obviously you can implement that condition using other software as well. But I don't have experience with Aspen Plus or Aspen Dynamics, how we implement that. But the offline planning, a majority of that we use MATLAB linear matrix inequality tools to solve the dissipated condition of the controller, which is required. And for the economic MPC and the differential dynamic stuff, then the implementation is much more complicated, because you need to do online optimization and online the integral with respect to the parameterization parameter S. We've been using a MATLAB to do that, but I think that there will be a way to implement these algorithms on other platforms.
Dr. Rashid, are you okay, or you have any other comment?
Sure, please.
I'm okay, sir. I'm okay.
Okay, sure. Yeah, thank you.
Yeah.
Thank you
Okay,
for
sir.
asking. Yeah.
Okay, thanks, sir.
Yeah. Professor G, there is another question here. Have you implemented the algorithm into pilot scale physical system, or maybe industrial scale physical system?
The short answer is we haven't yet. One of the reasons is that in our industrial, now we've been working on some industrial projects. One of the issues we have is that the capability of the existing control system hardware. So we actually in our projects we actually implemented the optimal control algorithms. So because we determine the control algorithms offline, and the online implementation is relatively simple, but the model predictive control, particularly the economic model predictive control, distributed model predictive control, that requires significant computational power of the control systems, and we haven't had an opportunity to test them on a physical process, but we should be able to test them using the pilot plan in my laboratory. But the only problem of that is it's just we don't have enough processor units. So we can do economic MPC, but not necessarily distributed economic MPC, because we don't have that many units in the part of the plan in my laboratory.
Sure. Okay. We have one more here. Prof. G, the conventional MPC, in terms of industrial application, they have an issue of the adaptation to the existing system, and sometimes the adaptation takes months or years to stabilize. So what you foresee to related to this algorithm on the industrial application? Any foreseen issues that maybe you can put forward?
Now, what I presented today, they are model based. So So I'm not exactly sure about the issue you're talking about. I think the issue you're talking about probably, I assume that you probably don't have a model, right, to start with, either. So you do some experiments to get, based on the response of the process, so you get these for example, linear models based on so using the system identification and use that models in the MPC design. Is that the case? In the questions. Yeah.
Yes.
So in that case, you fundamentally what you're talking about is the refinement or the improvement of the model you get over a period of time, because obviously one set or two sets of the experimental results may not give you a good model. The development we have so far mainly focused on the model based. So we assume that you have a good model to start with, and we did work out. I think I didn't list that paper in my presentation on the robust control, the plan-wide robust distributed robust control. So we assume that you got a model uncertainties. How do we deal with the model uncertainty? But the approach we developed using the dissipativity in that case was we used the dissipativity framework to deal with the interactions and the uncertainties in the same framework. But our approach does not improve over time. So it basically says, okay, now you have this sort of uncertainties, and how do we deal with that uncertainty, but does not improve over time. But if you want to do that improve over time, I think the dissipativity, now I don't have the results ready for you, but I think using dissipativity to ensure the stability is still very useful. Actually, one of the reasons why the dissipativity-based control was developed in 1980s was because of adaptive control. You know, in 1970s, 1980s, adaptive control were very, very hot at that time. And one of the problems of adaptive control is how you ensure stability. So I'm not sure whether the problem you're formulating, the question you just asked, is that related to the you are improving the model over time, and use the model for MPC, and so obviously what you have to do is that you have to recursively improve your model that is used in MPC. But the question here is that how do you ensure stability? And I would believe that you can use the dissipativity condition to ensure stability when the model is actually changing. So the idea is that even the model is changing, let's see whether what kind of dissipativity properties I have, and then we can derive the corresponding dissipativity condition for the controller to ensure stability. That was actually precisely the same idea in the adaptive control. The dissipativity was developed. The dissipativity theory was developed in 1980s. There is one book by Brian Anderson. I can't remember the title of the book and which year it was published, but he used I think he called it passivity at the time, not dissipativity, with the dissipativity condition to ensure the stability of the adaptive control systems. This idea also was developed in mechanical engineering quite some time ago, but because most of the mechanical systems are passive. So according to the dissipativity condition, if the process is passive and the controller is passive, of course you got strictly passive, for example. then you can ensure stability. So your controller can improve itself all the time without causing stability issues. A special example, of course, it's overly simplified case, is that adaptive PID control. Now, if you look at the passivity, so basically, no matter what kind of coefficients you have in the PID control, as long as you change the sign of the gain, and you don't change the sign of a KC, they are always passive. So if we use a passive, if we assume the process is passive, or a special case of dissipativeness, then you can have a PID controller. All the coefficients are adaptive, but you don't have a problem of stability because the stability is ensured by the dissipativity condition.
Sure.
So that's one of the ways. That's one of the ways you can think. Okay. Now I stop the sharing so I can see the question as well.
Yeah. We have another question here. If we add an observer to the control system, MPC control system, do we need to guarantee that the added observer also a dissipative subsystem?
Sorry, can you say the question again?
If we add the observer to the MPC system, do we need to make sure that this observer also dissipative subsystem?
I think no. In theory, no. But depending on the problem you're looking at, because if the system, if individual subsystems are observable, I don't think that's needed. Because we still have the separation principle. No, it should not be a problem. It could become a problem when each subsystem itself is not observable. Some states are not observable unless you have the information from another subsystem. In that case, we would have the dissipativity condition on the observer as well. We actually published a paper last year on that. Sorry, I didn't include that in the talk because that was for the monitoring. So it's about the distributed fault detection. So we actually have observers and fault detectors. So we have distributed fault detectors and observers. So when for each subsystem or for each unit we have one, and they talk to each other. Because in that case, if some states are not observable locally, but it's observable when you have the information from the other subsystems, then the dissipativity could be an issue. So we in that paper we actually have used we impose a dissipativity condition. But if the local system is fully observable, I think we don't need the observer to be dissipative, because the dissipative conditions are actually defined based on the input-output, particularly for MPC itself.
Yeah, sure. Okay. So it's now 1 p.m. Time flies. So I think we have to stop here. Otherwise, we will continue.
Yeah, I think
non-stop.
Yeah, I see another question here. Actually.
Okay. Hang on.
Does using a network of controllers instead of separate controllers make the control system less accurate, since there are multiple constraints involved? I don't think it would make the control system less accurate, but that you, in terms of optimality, plan-wide optimality, yes. So you would be less optimal. So I think just now, Zheng Yanghua posted a message. So he or she was saying that since each local controller seeks a maximum local minimum, it may or may not reach the global minimum. That's correct. That's correct. But it's not, we're not talking about the accuracy of control systems. I think we'll talk about the optimality of the plan-wide cost. So as I mentioned that the methods I mentioned, particularly self-interest economic, distributed economic MPC, they only optimize their own local cost functions. So from the point of view of the plan-wide cost, no, it's not optimal. But our recent work also, we developed that into the global cost to minimize the global cost, and using distributive conditions to help converging to the global cost. That in that case, we can still achieve the global optimality with reduced iterative optimizations. And also another interesting thing actually we found, personally I found is very interesting when we, that was in our paper published in IEEE control system letters, is that at that time we look at the self-interest distributed economic MPC. So every subsystem controller is optimizing its own selfish objectives. And certainly there's a question here whether there is a common good. And we found yes, even if you just want to maximize your own self-interest, there is still have a common good. So you could end up with a situation if we don't coordinate properly, then everybody end up with a position is that worse to themselves and worse to everybody.
Yeah. Okay. So Professor G and everyone, I think unfortunately I need to stop the Q&A here. It's 1 p.m. plus. Professor G, once again, thank you very much for your comprehensive presentation and very interesting. And thank you for your availability. We know that you are very busy. So thank you very much on behalf of the society and everyone. And everyone, thank you very much for joining us. Do remember to join us on the 21st of April for another webinar. But before we end, can I request everyone to turn on your video? So we will like to screenshot our videos.
Thank you very much, Agus, and the Process Control Society for inviting me. And thank you for engaging.
You hope to invite Dr. Joe for a second session later. This is only the first session.
Sure.
Okay.
Sure,
Thank you
Professor.
very much.
Yeah.
Dr. Hong is also here. His friend Dr. Hong from Vietnam is also attending this talk from Da Nang University. If he noticed it. Okay.
Yes.
Thank you.
Thank you, Professor.
Thank you very much.
Yeah, once again, Prof. G, thank you very much for being our webinar speakers. Hope to see you again soon in the near future.
Thank you. And I hope that I can collaborate with some of you in the future as well. And that's one of the, I showed the picture that we are 10 minutes from the beach.
Okay, sure. And everyone, thank you for joining. I'll see you again on 21st of April. So bye-bye from now and take care, everyone.